Okay, so this is the second part of the midterm review. So we'll continue to talk about sample midterm from spring 2019. And so right now we're looking at this question, analyzing running time for this function here. Okay, sorry. Mhm. Okay, so, oof. Okay, so we look at this function, okay, and this is obviously not a recursive function. So we have parameter that is an integer, take a positive value, and inside we have one step and then a while loop that will continue as long as n is greater than 1. Right, so every iteration of the loop, n is reduced by 1/3, and the step number is increased, and then at the end we return step. So this is unlike all other problems I've seen so far. So the key question, right? The key is, right, how many times does the while loop iterate? Okay, so that's a key thing, because other part of the code just contribute a constant amount of constant number of steps. So the key to this question is to figure out this question, which in turn translate to the following question, right? How many times do we need to divide n by 3 to get to 1, right? So that's a question, right? Supposedly, for example, right? So suppose n is 10, right? N divided by 3 will make n equal to 3, and do another division, we'll make n equal to 1. Okay, so this is what I would think about, right? So this is one iteration, another iteration. But in general, how do we calculate the number of times we need to divide n by 3 to get down to 1? So if you remember our discussion about logarithm, so let k be the number we're looking for, right? The number of times we're looking for. So then the question is, translate into n divided by 3 by how many times, right? Equal to 1. So you can solve this function to get k will need to be log base 3 of n. Okay, so this means, all right, so the total number of steps this function will execute is, right, so we take into account this step, that's 2, and then the number of times the inner loop is iterated is log 3 of n, and every iteration of the while loop have two steps, so that is the total number of computer steps. Okay, so now in terms of big O notation, right, remember what we're doing is basically looking at this expression, and then we figure out this is a constant and this is a log function of n. So this is dominating terms, so we drop the 2 and also drop this coefficient 2. So in the end, this is the growth rate of the function's running time. All right, so moving on. All right, so let's look at this function, okay? And this is given as a pseudocode, right? So we have a function 3, take a list as a parameter, and the So the body of the function will do the following, right? We'll call the same function on the left half of the list, and call the same function on the right half of the list, and then call the function on the middle half of the list. So this is what it looked like, all right? So this is called left half, and this is the right half. But what about the middle half? That means from here to here, okay? It's the middle half. But they're all called half because their length is all 1/3 of, half of n, right? The three halves we talk about, all their length is half of the total, which is n divided by 2. And after the three function call, we do some additional processing, right? We don't know the detail, but we know the amount of time take here is n squared. So what's the overall running time for the whole function call, right? So again, let's T of n represent the total number of steps during function 3 with this size input, right? So this is what it represents, okay? And let's try to write an expression for T sub n based upon our analysis of the pseudocode here, okay? So when the list size is n, right, how many steps totally is taken? So let's look at the first step is call the same function on first half of the list. So that is a function call, right? And because it's the same function call, that means the same running time function applied to this call also. But its size is not n anymore. It's really the size of the left half, which is n over 2. Okay, so this is total number step it takes to complete this part, right? So similarly, right, the second part is also the same function call, so the same running time function. The size of input is n over 2, and the third is also n over 2. Okay, so far we have taken care of this, and this. So the last part, some additional processing, but we know the time is n squared. Okay, so that's all, right? So combining same terms, right, we get 3t over n over 2 plus n squared. Okay, so this recursive formula, we could use a master theorem, right? Okay, so the key is to find out what is A, what is B, and what is D. Okay, so remember A is how many subproblems, so for our case is 3, and B is the ratio that the problem size decreased, so n over 2, right? So every subproblem is half the size, and our D is 2. Okay, so now we just plug in our master theorem, right, which we have provided in the very beginning of the midterm exam. Okay, so we will see compare D, right, which is 2 versus log B of A, right? So plug in our number, that is log 2 of 3. So which one is bigger? So I think for this you have to know that log 2, right, sorry, so you need to say this, right, which is 2. So because we need to compare 2 with this number, all right, so therefore we try to compare, put a sign here, right, and 2 would be here. Okay, so in the end, log 203 is less than log base 204. So therefore, we have less than relation between the two. Okay, so this means we are in case number 1. Therefore, T sub n is log base 2 of n to the 2, right? The D here. So because this is bigger than this one, so D, right, the larger value appear here. Okay, so this problem is done. All right, so let's look at this coding question. Okay, we are asking you to write a function that calculate a Fibonacci sequence number, and the requirement is the running time need to be linear and the space requirement need to be constant. So please review, right? You need to review lecture number 1 and 2, where we go through 2 different ways to solve this problem. Okay, right. Solution number 1, right, is a recursive way, and the running time is, and I think something like that. Okay, it's exponential. Right, actually, it should be this simple. Okay, so it's definitely not does not meet our requirement. And the second one is iterative solution, in which the running time is linear, but the space required is also linear, right? So in this solution, we have included in the slides, we use a particular array of 1 to n to store sequence f, Fibonacci sequence. So now current problem's challenge is use constant space. Right. So what I will do is I will give you the code, right? The idea I'm going to talk about soon. Next, so we have a Fibonacci function, right? Parameters n, right? So like before, if n is 0, return 0. If n is 1, return 1. For other cases, all right, we'll use, right, we're going to recycle 2 parameter, right, 2 variable. We call the previous, okay, and the previous, we got 1. So initially, they're set to the f of 0, f of 1, all right, and then we're going to enter a for loop, all right, so this is line 1, 2, 3, okay, so line 4, which continue from here, is this following, right, for I start from 2 to n, so we're going to calculate all the number in the sequence from 2, 3, all the way to n, which is our target number to find out. Okay, so we're going to always use previous 2 value, right? So that is PREV plus PREV, PREV, right? So this is based on the pattern in the sequence. So every number, right? So this is F0, F1. So F2 would be the sum of these 2 number, right? So, okay, so in the very beginning, PP is this, previous, current is this, right? Now, suppose I want to move to the next step. So essentially, last time's previous should become my previous period for this one, and previous times current should become previous. So this is a kind of update to next step, okay, to make sure to get ready for the next step calculation. So we will say, okay, now after this, before I go to the next i's value, I need to make so this is what I need to do, right? I need to forget about the previous update with previous and update previous to be the current value in current. Okay, so this part will be repeated, right, until I is counted up to n, right? In the end, you just need to return current. So if you have question about how this works, I highly recommend you to trace through, right? So for you to understand this, right, trace execution of variable maybe 5, right, to see how it works, how we just use 3 variables to move our way up to the value we want to calculate. So that's right. So question number 4 is a test from quicksort. Okay, so we have studied this question before. This problem before. It's substantial in class. And let me try to remember. Okay, so you see here we use the first element in the array as our pivot value. Okay. Treat the first addition call on the above quicksort when the above quicksort is called to sort the following array. Okay. Alright, so this is shouldn't be too bad. Okay, so this is our input. We just want to see follow through this first call to partition. Alright. Okay, so the essential thing to do is to realize my first is set to 1, alright, and last is set to 8. Okay, and let's trace keep track the variables value by drawing a box. Alright, x is initialized to be a first, so it will be set to 6. So right now I move to the next statement. I will be set to first minus 1, so it's 0. So you can visually just draw I to be here to indicate it's pointing to the 0th place. So J will start from first, which is 1. Okay. If AJ is less than equal to X, right? If AJ so it's less than, so right now I'm in this code. Oh, I mean this line. AJ, which is 6, right? Compare with X, 6 is equal. So what do we do? So that means this condition is true. I is incremented, so I will be here. The value is updated to I. And then swap AI with AJ, so that nothing, maybe swap AI with AJ, nothing will happen, no change will be made. So now we back to this loop, and J is incremented to 2. So now compare A of 2, which will be 1 against 6, right, again X. So still less, so I will be again increased, and we'll swap AI with AJ, again no change to the variable's value. So move on to J equal to 3, Right, so a sub 3 is 4, right? It's still less than equal to x greater than 6. So I will be increased to 3, and swap AI AJ, nothing happened. Okay, so now J will be 4. A sub 4 is 1, 2, 3, 4. A sub 4 is here, right? So still less, right? And that means we'll increase I again to be 4. Swap AI with AJ, no effect. Okay, now J will be updated to be 5. Okay, still same situation. Okay, so increment I to be 5. Swap AI with AJ, no effect. Now J will be here, 6. 6 is still less than equal to x. Oh, right, I'm sorry. A sub 2, A sub 6 is 2, right? So A sub 6 is 2. It's still less than equal to our pivot value. So I will be increased to 6, all right? Swap AI AJ, nothing happened. And now J is 7. Okay, so we are here now. So finally, A sub 7 is not, it's greater than 6. Okay, so that means I don't go into this body of the if statement. So nothing will happen to I. So J will be incremented to the last. So A sub J is greater than 6. So also nothing happened. So J will be finally greater than last. So what happened next is, right, I think here we need to, is we're going to swap AI plus 1. So remember I is 6. 1, 2, 3, 4, 5, 6. So I will be here. Right, so I is pointing to the last elements that are, sorry, I think I screw up because I didn't realize the last element is greater than 6. So I hope this show you enough. I'm going to skip this one. So hopefully you'll be able to carry it out without making mistake like I do. Okay. Given the input instant to quicksort that yield the worst case performance, right? So I think the thing to remember is that we're using the first element as our pivot value. So you can say that an example that gives you the worst case performance would be when the list is fully sorted already, right? So for example, so the first partition, right, because I use this value as our pivot value, so what happened is that end up the pivot value partition function will return 1, right, which is the location of the pivot value, and okay, so this part is all the value, the part that's contain value that are greater than 1. Okay, and you can imagine now, right, in the 2 recursive call, the first part is empty, right? Empty partition here, because no value is less than equal to 1 except the only one here. So again, the next iteration, right, when we try to quicksort this part, again, the smallest element will be used as a pivot value, right? So we'll be stuck into this pattern of running time. Okay, so every partition takes n, right? But every time I end up with two partition, one size 0, another part size n-1. So solve this one, we get t sub n equal to theta n square. Okay, I'm going to stop here for now. Okay.